So, SRP, right? It's all about ensuring that a class has only one reason to change. Like, if you have a class for calculating payroll, and it also sends out emails, then you're in trouble when something changes.
Yeah, I've seen classes like that before. They become hard to maintain.
Exactly. And it's not just maintenance. When you have multiple responsibilities in one class, testing becomes a nightmare too. Imagine trying to test email functionality while dealing with complex payroll calculations. You end up writing tests that are way more complicated than they need to be.
That sounds pretty messy.
Oh, it gets worse. Let me tell you about this project I was on where we had a single class doing everything from database access to user interface rendering. The codebase was a mess. Every small change required touching the same file over and over again.
Sounds like a lot of unnecessary dependencies.
Absolutely. Dependencies make your system fragile. If one part fails, it can bring down the whole thing. Plus, it's harder to understand what each piece does when there are so many responsibilities bundled together.
Makes sense. So separating those concerns would help?
Definitely. Each component should do one thing well and be independent of others as much as possible. For example, if you have a payment processing module, it shouldn't care whether an email is sent or not after the transaction completes. Those are separate concerns.
But how do you decide what goes where?
Good, good question. One approach is to think about use cases and group-related functionalities together, based on their purpose rather than technical details. Another is to look at potential failure points. Where could things go wrong? And design around minimizing those risks.
That seems logical.
And don't forget about future-proofing your design. By adhering to SRP, you're making sure that any new feature or change can be implemented without disrupting existing parts of the system.
That would definitely save time in the long run.
Time and headaches. Keeping things simple and focused reduces complexity overall, which means fewer bugs and easier upgrades later on. Now imagine applying this principle across an entire code base. Speaking of reducing complexity and making upgrades easier, let's talk about the open-closed principle. Have you ever worked on a project where adding new features felt like stepping into a minefield?
Yeah, that happened once. Every new feature seemed to break something else.
Exactly. The open-close principle says that software entities should be open for extension, but closed for modification. This means you can add new behaviors or functionalities without changing existing code.
That sounds ideal.
It is. One practical way to achieve this is through inheritance and polymorphism. For instance, say you have a base class shape with methods like draw. Instead of modifying this class every time you want to add a new shape type, you create subclasses like circle, square, etc., each implementing its own version of draw.
So instead of changing the original code, you extend it?
Precisely. And it keeps your core logic intact, which is crucial for maintaining stability and reliability. Plus, it makes your code more modular and easier to test.
That makes sense. How do you decide when to use this principle, though?
Well, typically when you foresee frequent changes in certain parts of your application. For example, if you know there will be different types of shapes in a drawing app, designing the system around the open-close principle from the start can save a lot of headache down the line.
I see. So it's about anticipating future needs and planning accordingly.
Absolutely. It's all about setting up your architecture in a way that allows flexibility while preserving the integrity of the existing code base. Think of it as building a house with expandable rooms instead of fixed walls.
That's a good analogy.
And don't forget, applying these principles isn't always straightforward. Sometimes you need to refactor existing code to fit them better. But in the long run, it pays off tremendously in terms of maintainability and scalability. Absolutely. And speaking of refactoring and maintaining code, Let's talk about the Liskov substitution principle. Have you ever encountered a situation where subclassing went wrong and broke your code?
Yeah. I remember once when a subclass didn't behave the same way as the base class, causing some unexpected issues.
Right. The Liskov substitution principle states that objects of a superclass shall be replaceable with objects of its subclasses without breaking the application. Essentially, it means that a subclass should be able to stand in for its superclass without any adverse effects.
That sounds like a tricky balance to maintain.
It can be, especially in larger code bases. For instance, if you have a vehicle class and subclasses like car and bike, each subclass should respect the contract defined by vehicle. If car suddenly starts behaving differently in ways that aren't expected by vehicle, you're violating the principle.
So ensuring consistency across subclasses is key.
Exactly. One common pitfall is overriding methods in a way that doesn't adhere to the superclass's preconditions and postconditions. For example, if a vehicle has a method startEngine that assumes certain actions happen consistently, then both car startEngine and bike startEngine should uphold those assumptions.
That makes sense. It's about keeping behaviors consistent.
Yes, and this often requires careful design upfront. You need to define clear contracts for your base classes so that subclasses know exactly what they are supposed to implement. This helps prevent bugs and ensures that your code remains robust even as it grows or changes over time.
So defining clear interfaces is crucial.
Definitely. Clear interfaces help ensure that subclasses behave correctly and predictably. And definitely. Speaking of clear interfaces, let's talk about the interface segregation principle. Have you ever worked with a large interface that had methods you didn't need?
Yeah, I've seen that before. It feels like you're carrying around extra baggage you don't use.
Exactly. The interface segregation principle states that no client should be forced to depend on methods it does not use. In other words, it's better to have many specific small interfaces than one general-purpose big interface.
That sounds like it could simplify things a lot.
It really can. For example, if you have an order processor interface with methods like process payment, send a mail, and update inventory, but some clients only need to process payments without sending emails or updating inventory, those clients are burdened with unused methods.
So splitting the interface would help?
Absolutely. You could split it into smaller interfaces like payment processor, email sender, and inventory updater. This way, each client implements only the methods it needs. It makes your code cleaner and more modular.
That seems like it would reduce coupling as well.
Definitely. Reducing coupling is a huge benefit. Each part of your system becomes more independent and easier to manage. But there are challenges too. Managing multiple small interfaces can get complex, especially in large projects where the number of interfaces might grow rapidly.
That makes sense. Keeping track of them all could be tricky.
It can be. You need good naming conventions and organization to keep things manageable. Another challenge is that developers might sometimes over-engineer by creating overly fine-grained interfaces that don't provide much value in return for added complexity.
Finding the right balance must be key.
Exactly. Balancing simplicity and granularity is crucial. You want to avoid both monolithic interfaces and overly fragmented ones. Getting this right often requires experience and a bit of trial and error, but it pays off in terms of maintainability and flexibility of your code base.